Hey everyone, welcome back to Advent of Code, Day 13. Advent of Code is a 25-day coding challenge that happens every December from December 1st to December 25th. Instead of getting little nuggets of chocolate, you get little nuggets of brain joy. That's a terrible way of phrasing that. We'll never talk about this again. These are usually themed around trying to make a Christmas happen, to save Christmas. This year, we're taking it easy. It's 2020. We need to relax a little bit. The lore is we're going on vacation. So let's get into where we are so far. We were on a ferry. Your ferry and we just navigated our ferry through treacherous waters. Your ferry can make it safely to a nearby port, but it won't get much further. When you call to book another ship, you discover that no ships embark from that port in your vacation to your vacation. Let me hold on a second. Can I read? Can I read? Reading is hard. Your ferry can make it safely to a nearby port, but it won't get much further. When you call to book another ship, you discover that no ships embark from that port to your vacation island. That's terrible. You'll need to get from the port to the nearest airport. Interesting. Fortunately, a shuttle bus service is available to bring you from the seaport to the airport. Each bus has an ID number that also indicates how often the bus leaves for the airport. Bus schedules are defined based off a timestamp that measures the number of minutes since some fixed reference point in the past. At timestamp 0, every bus simultaneously departed from the seaport. After that, each bus travels to the airport, then various other locations, and finally returns to the seaport to repeat its journey forever. So they're on a loop. Okay. The time this loop takes a particular bus is also its ID number. The bus with ID 5 departs from the seaport at timestamps 0, 5, 10, 15. Okay. The bus with ID 11 departs at 0, 11, 22, 33, and so on. If you are there when the bus departs, you can ride that bus to the airport. Your notes, your puzzle input, consists of 2 lines. The first line is your estimate of the earliest timestamp that you could depart on a bus. Okay. The second line lists the bus IDs that are in service according to the shuttle company. Entries that show X must be out of service. Second line lists... Okay, so X indicates that they're out of service. Okay. So you decide to ignore them. To save time, once you arrive, your goal is to figure out the earliest bus that you can take to the airport. There will be exactly one such bus. For example, suppose you have the following nodes. 9:39, 7, and then as 9:39 is the earliest timestamp I could depart on a bus. And then we have a number of comma-separated amount of times it takes for the bus to take a loop. So we'll have 7, 13, 59, 31, 19. I think those are all prime. Okay. I think those are all prime. Yeah. Five plus 9, that's 13. Yeah, so that's not divisible by 3. Obviously not by 2. I don't know about the 59 off the top of my head, but I think I'm pretty sure off the top of my head everything else is. And 59 could be 2. Here's the earliest timestamp that you could depart from. Here's the earliest timestamp you could depart. Okay, so this is just saying what we just went through. Near timestamp 939, these bus IDs depart at the times marked D. Sure, yeah, so these loop over and over again. So basically we're fine in order to figure out the times that buses depart from our origin, we have to basically find multiples of these numbers and find the lowest one that is greater than or equal to 939, right? That sounds about right. The earliest bus you could take is 59. doesn't depart until 9:44, so you would need to wait 5 minutes before it departs. Multiplying the bus ID by the number of minutes you'll need to wait. It gives you 295. Okay, so this first part's really straightforward. Actually, I gave an interview recently where I expected people to do similar problems to this, so I'm kind of familiar with like the basic algorithm we need for this. So we're gonna have our normal input lines. For once, we're not going through like the entire. Okay, so first things first. Let's make a sample input. First things first, we'll make a sample input based off of what we have here. Our real input will be very similar. I imagine the second line will be very long for the second one. We don't need those files. We do need this file, though. So input lines gives us each... It basically takes the entire list of... the entire contents of input sample and arrayifies it. And takes off any new lines because we never care about that, right? Yeah. So this is always going to return exactly a 2-element array. So earliest start and schedules. So in Ruby, that will just separate those out. And let's get the buses. So for that, we're going to take schedules CSV. We're going to split it on comma because this is a comma separated thing. We're going to reject is it x or lowercase x? Oh, it's lowercase x. Okay. I have a feeling we're going to be doing something more interesting with those x's for part 2. That's my hunch. And for good measure, we're going to turn these all into integers because we need to treat them like integers because we're going to be multiplying them and all that good jazz. Okay, so I mean we can generally assume that these are going to be unique, but we can also throw a unique on here because we don't really care about duplicate ones. And let's also sort them. The sorting's not all that important. But it might make it a little easier for us to read what's going on. So we actually do need to know there might be a way that we can immediately zoom to like the 239 value, but I'm not going to do that. I think we're just going to take the lazy approach and iterate up from 0. So we're just going to loop through until we find a bus. Oh wait, we can actually just iterate infinitely. That might actually be a nicer way to do this. Let me see if I remember the syntax for this. Okay, so that just goes infinitely. Okay, so we can just use an infinite range here because we actually need the index here. And I don't know why, actually we don't even need to... Oh god, I'm actually dumb here. Okay, we don't need to do that. We don't need to start from 0. There's no reason ever to start from 0. We're actually just testing the modulus, because if there's no... Just mod and then multiply. Exactly. I don't know why I was thinking that we need to do that other thing, Jelly Rat. That's just really cringe. We're not going to do that. So first of all, let's take the earliest start and turn that into an integer as well. So we're going to take earliest start. We're going to go up infinitely. And don't need this anymore. Well, let's hold on to that for now. Matching bus equals buses. Detect. I'm running out of variable names here. Oh god. Scheduled bus. So we want to find the first one where the first scheduled bus There we go. I think I like this naming better. So, early start, we don't know if these are actually buses, so let's just call them potential buses. Matching bus. If the potential bus mod a real bus is 0. Find the first and the first bus that's a multiple of any scheduled buses. Let's get rid of that. I don't think we actually matching bus in the outer scope. I think that let's break if matching bus. And otherwise it'll just keep on going and going and going forever and ever until the end of time. Okay, so now let's just matching bus. Matching bus. I think the scope lets us do that. Because it's not like actually a sub, it's just a block. Let's get into day 13. And we're going to just run this real quick. We did something wrong here. We did something terrible. Okay, so we actually do need to declare the matching bus before. That doesn't make sense. Earliest start we should never actually... Oh, do we need more than that? Okay, so we need the earliest bus that you could possibly take. And we need the timestamp. Okay, that's easy enough. I think it's to just like for the structure of the program, it's going to be a little more easy if we just throw this into a different method. Find bus. Or start. Buses. I think that's all we need for that. Let's pull this all out. If matching bus, we're going to return. Yeah, potential bus. Bus is actually terrible. Time. Better name for that, right? Time and bus. That's a little dirty because we're breaking out of a loop with a return, which is a little cringe, but that's fine. Now, if we never... If somehow it gets out of this infinite loop, then something terrible happened, right? So... Find bus. Bus. Or actually a time bus. Earliest start. And buses. Bus at time. And we want to multiply these together. No, we need to subtract. Time minus earliest. Result. So that would be time minus earliest start. And that's multiplied by the ID of the bus, right? Yeah, totally. So let's see if we screwed anything up here. Yeah, we still screwed stuff up. Undefined local variable bus. Right, because we renamed this variable. Or did we? What line is this on? 28? That's when we're just running the program, I think. Oh wait, no. Oh. This needs to be matching bus. Because bus is just local to this block here, so it would never see that. Yeah, that makes sense. Okay, let's go. Okay, so 944. That's what we expect. We're taking 59. 59, that matches. And 259. 259. So we match entirely up right now. So I think that that the solution, I feel pretty good about the solution right now. Let's do it with the actual input. We'll just throw that into our project here. I need to open up this. So we're starting off a bit higher, and we have quite a few more buses to contend with. Many of those x's, I'm wondering what we're going to be doing with the x's in part 2. That's going to be interesting. We'll just turn this into input because we're not running on our sample anymore. Let's rerun this and see how we do. Okay, so let's see if this bus actually makes sense. 397, that's actually a real bus. And what's this? Thousands, million. thousands, million. So this is about 6 minutes after. So that all looks like it's plausible. Obviously, I'm not doing this by hand, so I don't know for sure if that's correct. But it seems plausible. Let's throw this into our answer and see if we get timed out or not. That's I think I don't see any reason why this would be wrong, though. Okay, great. We get another gold star. We get to continue. Let's see what we're doing next. The shuttle company is running a contest. 1 gold coin for anyone who can find the earliest timestamp, such that the first bus ID departs at the time. 1 gold coin for anyone that can find the earliest timestamp, such that the first bus ID departs at that time, and each subsequent listed bus ID departs at that subsequent moment. First line of your input is no longer relevant. Oh, okay, well, okay, just ignore the first line. Relevant now. For example, suppose you have the same list of bus IDs as above: 713, XX, 59, 31, 19. An X in the schedule means there are no constraints on what bus ID must depart at what time at that time. Okay. Interesting. So any bus can depart at X. It can depart at an X time. This means you are looking for the earliest timestamp, call it T, such that bus 7 departs at timestamp T. Bus 13 departs 1 minute after timestamp T. There are no requirements or restrictions on departures at 2 or 3 moments after timestamp. So do they still depart at multiples of each other, though? There are no requirements or restraints after. Bus ID 59 departs 4 minutes after timestamp T. How do we know that? There are no requirements or restrictions on departures at 5 minutes after the timestamp T. Bus ID 31 departs 6 minutes after timestamp T. It's due to appear in the input. Bus ID 19 departs. Okay, so I definitely want to get rid of the sort. The sort was a terrible idea. Let's get rid of the sort. There are no requirements. Okay, so bus 6 minutes after. Okay. Bus ID 19 departs 7 minutes after T. The only bus departures that matter are listed in the bus IDs at their specified offsets from T. Those bus IDs can depart at other times, and other bus IDs can depart at those times. For example, in the list above, because bus ID 19 must depart 7 minutes after the timestamp at which bus ID 7 departs, bus ID 7 will always also be departing with bus ID 19 at 7 minutes after timestamp T. Example, the earliest timestamp will be that big number. In the above example, bus ID 7 departs at timestamp that 7 minutes after T. Fine. The only requirement on that minute is that the bus ID 19 departs then, and it does. Here's some other examples. The earliest timestamp that matches the list. 7x 1319 3417. So many bus IDs on your list. Surely the actual earliest timestamp will be larger than a very big number. Okay. What is the earliest timestamp such that all of the listed bus IDs depart at offsets matching their positions on the list? Okay. Okay, I'm going to read through this again, just to try to rock exactly what's going on here. That there are no constraints on what bus IDs must depart at the time. Okay. You're looking at the earliest timestamp. Bus ID 7 departs at 13 is 1 after 2. There are no requirements for... Try and find the earliest timestamp such that the first bus ID departs at the time each subsequent listed bus ID departs at a subsequent time. Okay. The X's still seem kind of weird to me, but I think we were just ignoring them for now because these are all like primes of each other anyway, so you can't really flip them in like that. Okay, so okay, I'm getting it now. So we're trying to find something where bus 7 appears, then bus 13 appears a minute later, and then bus 59 appears a few minutes later, 3 minutes later, or 2 minutes later? 3 minutes later. And then bus 31 appears 2 minutes later, and bus 19 appears 1 minute after that. Okay. I'm understanding the problem. It takes me a minute, especially when I'm like on stream, to really grok what a problem is, because, you know, word problems and sometimes talking to yourself and reading silently are very different things from how you comprehend things. Okay. This is gonna be like a really big number, right? I wonder if I feel like there's probably like some sort of like weird math algorithm that I don't know about that will instantaneously just like give you like the right number and constant speed, but I don't know that algorithm. I'm not gonna. I'm not gonna fret too much about that. So first thing we can do to kind of like limit down. The first thing we can do. First of all, we don't care about. Let's make a copy of our problem 1, problem 2, so that we don't clobber our first solution. We have it for posterity. We don't care about earliest start at all. We're ignoring that entirely. We got rid of the sort because we actually do care a whole lot about the order that these are in. I think we want a little bit of a different structure for this. Yeah, I think we kind of like want to have a structure where we can just like test all of these at once. In terms of their offset, I think. Yeah. Let's start off with this. Gonna start off with our schedules CSV here. We're not gonna worry about doing this. This is all going away. And we're gonna split our schedules. Still 1 comma each with index. So this is going to be the scheduled value. It's going to be a bus. This is going to be an index. We're going to key this off and create like a little lambda here. Actually, this is going to be a... don't want the double do there. That's bad. Have this test. Let's actually have keep a... You don't need to do that cast repeatedly. Actually, that's kind of ugly. Let's just do this. I don't really care about the variable. We can change the type. We know what we're doing here. We don't need to worry about being super clean. Okay, so what we're going to do is we're going to see if... I think for our first very naive approach, what we're going to do is we're just going to loop through values and have it test each element in this hash that we're building up here. And the hash is going to have a little callback that will let us test, and it'll remember kind of like what index it was at. We want to skip if this is... We're going to skip our x's, but the index will still be going up, so it's fine. Of plus integer, and that maps to time being tested. Tested. True, false. If valid time bus. Didn't see. That sounds pretty reasonable. And then we'll return our hash here. And we'll just get our schedules hash here. Does anything need to be turned into integer that I'm missing here? I don't think so. I think we got everything here. Schedules to hash. Let's adjust, get rid of all of this. Actually, I think find bus entirely. We might be able to reuse some of this implementation. Find matching time. And we're just going to have our buses hash here. We're just going to print out whatever we get here, because I'm let's just try this out initially and see what we come up with. Okay. What do I rename this to? I rename this to find matching time. You would think after so many years I would finally be okay with my Vim key binding, so I wouldn't just type out P's sporadically when I don't need them. Oh, good grief. So we're gonna just start with we're gonna start with 0 and just go all the way up. We could technically also start with max of the bus hashes key, but that doesn't matter at all, right? It's in terms of big O, that doesn't matter. We're cutting off a handful of times usually, right? Just actually looking at the input. Oh, this actually might be a little significant. Yeah. We'll actually do that. Because these are not going to appear in sequence. Well, actually, I guess they technically could. It could be the first instance of 983 could be the... No, because that would mean that it's only 2, 3, 4, 5, 6, 7. It's maybe 20 after 17, so that's never going to be true, right? That's never going to be true. So yes, let's just as a slight optimization. Oh, I'm in problem 1. Let's get rid of that. Get rid of that. We don't need that. Make sure we don't get into there accidentally. Last bus. Bus is ish. Is max. And we're gonna go up infinitely. My big concern is I think this is gonna be super slow, and it's just gonna not really return anything meaningful. So we're gonna iterate over time. And if buses hash all, bus proc. The bus part actually doesn't even matter, does it? The structure actually could have been just an array, probably, couldn't it? An array of lambdas. No, but we not really though, because we still kind of need the last bus. So not really. That's fine though. That would have been an interesting structure though, for sure. Bus proc. Okay, so we're calling proc on time, and we're basically saying that if all these are true, then we're really happy. Because we matched everything. Otherwise, we just continue on this wild roller coaster forever. And we're already printing in this out up here. Okay, I feel like it's gonna be super slow, so I just kind of like want to print something repeatedly so that it feels like we're doing something. Still going. Just a little thing so I know, like, hey, we didn't crash. We're still in there. We're still in there, slugger. So that's gonna print out every 1,000. So we'll also we'll kind of have some visualization of like how fast or slow my example is here. Let's actually run this with the sample though. Let's run this with the sample input to start. And make sure that our logic is generally sound. Let's run problem 2. Unexpected do. You hate to see it. 14. Oh, I don't know why. Yeah, no, that's very odd. We should not have that there. Undefined local variable buses. Let's see where we have the. I think 50 is just our main call. 8, I think is just as. Yeah, it's just top of our thing. 32. Oh, we called this buses hash. We didn't call it buses. Okay, let's see what other syntax errors we have. Undefined method hash. On 32, what does that look like? And 32, that's here. Oh, I was dumb. I was so dumb. That's supposed to be an underline. That's not a dot. What am I doing here? Oh wow, this is really big for what's the expected for the sample input? Okay, so we're not actually supposed to be at the sample input yet, so that's fine. Also, shouldn't this only be printing out when it's... Oh, I'm printing out way too much, am I? Oh, this should only be printing out when it's like mod 1000, right? God, let me scroll down. Okay, so we found a number. I think that our print statement was junk. That was not good, but oh, this is always going. 0 is true. That's why this such junk. Read the whole description, by the way. However, surely your actual earliest timestamp will be larger than. Yeah, I know there's probably like a mathy way to do this in a way that's much nicer. I'm just starting off with the brute force, and I imagine that it's going to be terrible. I anticipate it being terrible. I did see that bit, though. I guess what we could do instead is... I'm going to run on the sample first. I'm going to run on the actual thing first. To confirm that it's actually terrible. But I'm pretty sure this will be terrible. But while that's running, we can think a little bit about what this is going to end up looking like. So what we could potentially do is we can calculate multiples of all of the numbers we have in play. we can calculate the multiples of all these. I feel like there has to be like some sort of like weird like discrete math thing that just like turns this into a constant time algorithm though. That maybe I don't actually know. It almost feels like proof by induction. Just the way the setup is. This is gonna be running for a little bit. Well, it's running. The problem that we essentially have is that we have x, y, a. See, we have like all these prime factors. Well, I don't even know if they're prime. I think in the samples I saw they were prime. I guess what one thing I could do as simplification is cut out anything that can come in multiples, I guess. But no, I don't think that's actually... One, I think these are all prime, and two, I don't think that is going to... That's not useful, I don't think. We're trying to solve for a case where, like, for t, t mod x 0, t I plus 1 is 0, t mod z is plus 2, that these all add up to 0. Still going. One thing we could do is set our starting time, the first thing that we're checking, to be higher. I don't know if there's any good reason to believe that like the product of everything is going to... that where this is all going to line up is going to be bigger than the product of all these, but we could try that. That's something we could definitely do. We could also take the problem literally, right? We could do this. We could just say... Oh. Can I copy paste? Yes, I can. We could take this literally, right? Are we already above that number, though? We might already be above that number. What's this? Thousands, millions, billions, trillions? Yeah. So we're definitely not nowhere near that yet. So let's just try it with a really big start and see if we get something quick. Printing is always going to slow us down, so let's... do this. I might have added too many zeros there. I might still have too many zeros there. Okay, now we're talking. Out of curiosity, I'm kind of curious what the product is of all these. How big of a number? If we start with that, how big of a number we'd be looking at? $17, $41, $983, $9, $19. $7, $37, $13. Okay, so that's a bit bigger. I wonder if there's any like algebra properties that deal with modulus. You don't really see them that much in most classes. Because I mean, like technically, we could say something like, suppose we have two factors, x and y. We want equals n times x, p plus 1 equals actually let's different variables here. Q times y. Would we be able to solve for this? We only have two equations. We have three variables. So in this case, equals q times y minus 1 equals times x. So essentially, I think we're still short an algorithm here. We're short an equation here to solve for this. Although I guess we do know what we're trying to solve for arbitrary x and y. Those are x and y are constants. So I mean, like if we were dealing with like this literally, let's actually just use the sample input. We basically have the equation equals 7 x times 7 p plus 1 equals y times 13, t plus 2, we don't care about t plus 2, t plus 3, we don't care about t plus 3, t plus 4 equals z times 59, t plus 6 equals, let's just loop around, a times 31, t plus 7 equals b times 19. Do we have enough equations to solve for this? We only have, yeah, because there's only one variable per equation. Oh no, there's n variables plus 1, where n is the number of equations that we have. So we do know that 7x equals 13y minus 1 equals 59z minus 4 equals 31a minus 6 equals 19b minus 7. What is that by us? Well, okay, so in the case of 7x equals 13y, does zeroing out make sense here? I think I'm on the wrong path here. or the right path, and I'm just like looking at it weird. So, I mean, like, we could technically say 7x or y divided by 13. And we also know that 7x equals 59z minus 4. Oh, that's gross. So actually, if we flip this around, we solve for x instead. X equals 13y minus 1 divided by 7. And we also know that 7x is 59z minus 4. But we already knew that 59z minus 4 equals 13y minus 1. Still going, by the way. Still going. The solution that will never work is still going. I'm gonna rewrite these. Make it a little more, because ultimately we're solving for t. We do know that we can add all these together. 1, 2, 3, 4, 5. 5t equals 7x. Y. How big is my jump? My jump, I set it for like the thing they actually put as the literal there. I jumped up by that much. So I think that's, we counted out earlier. I'm not gonna count out the zeros again. I think it's like 100 billion, something like that. Oh, for each iteration, I'm going up by. I'm going up by 1 each time. So that's obviously not the solution. Well, yeah, I'm initially going up. Yeah, I mean, I can't always go up by 17. That's true. That's true. That is a valid point. That is a valid point. I appreciate the suggestion. We can iterate by this 900 number instead. So if we start from 0 and increment by that, that should still be faster than going by 1. After you find the right x mod 7 equals 0, change the step times equals current bus. We're gonna, at the very least, what we're gonna do is change this up a little bit. While true, let's say that last bus is 0 because we want to make sure that we're a multiple of if we're going to be going up multiples of our largest number, I want to make sure that I'm mod of that. Take this apart a little bit. In the end, we're gonna last bus plus equals largest. Get rid of that, or rather, time plus equal plus equals largest. Let's see what this looks like. we jump up so high all of a sudden? That seems weird to me. What is that? That doesn't seem right. It's multiples of 93 and one with many zeros. I don't see why it would be doing that though. Because we set time to 0 and we're just adding. Yeah, but time is 0 initially, and then we're just adding on the largest value from the list of buses that we have. Like, oh, that's right, because it's only displaying it when it's a multiple of. Okay, now I get it. Now I get it. Now I get it. Now I get it. That makes a whole lot of sense. Because I'm not printing it out every time. That makes a whole lot of sense. But how high up are we now? This is the final input, not the sample one. We know our algorithm works generally for the sample input, just the actual input is a lot bigger, so brute force isn't working as well for that. That's why I was looking to see if like there was an algebraic way to just kind of like simplify everything for a bit. I think if there's something. I mean, this is definitely not the optimal solution. I think we can all agree on that. Oh wait, we actually don't want times that are just multiples of our P max. Now that I'm thinking about it. Because P max is going to be plus some sort of offset. So we actually need to adjust this a bit. Oh, we don't actually have the data we need to do this. That's really unfortunate. Max plus the mod that we want to test. Yeah, exactly. I'm just realizing that now that. Yeah, this one's definitely like definitely the most challenging one we've encountered so far, Glenn, for sure. So let's modify our structure a little bit because I think I actually do need. Oh, this data structure is going to get so gross. Let's do this. Because we need to add on the index that we're looking at. Most solutions on Reddit say, I had to look up redacted to solve this. Tell me if you want to unredact that. I'm not giving up yet, Glenn, but I'm getting pretty close, I think. I feel really confident that there is some sort of like very simple mathematical way to just do this, and the fact that I haven't taken anything besides any math courses outside of calculus in a very long time, uh, I wouldn't call it simple. Tell me this, Glenn. After you unredact that, is it simple after that? Is it like free after that, or is it like actually implementing it well is very difficult? It's an algorithm that has a Rosetta code page. I don't know what Rosetta code is, but I'm guessing that that's a wiki that has like a extensive list of like complicated, interesting algorithms. I'm guessing. I need to adjust this over here. Wait. That. It's a Rosetta Stone of programming language. Oh, that's cool. That's cool. I'm not familiar with that. I'll have to check that out for sure. Oh god, this feels bad. Am I gonna this? Is this gonna be the first one where I don't really have like a real spoiler? Oh, that's cool. That's cool. Let's. So it just kind of like it takes like every. Okay, so it has like a basics of like whatever algorithm this page is supposed to be about, and you said like, oh, and it has it in. Wow, it's a lot of these are a lot of languages here. That's really cool. So what you're telling me is that once some of more yeah, obviously Fibonacci is like such like a fundamental sequence that obviously everyone is going to every language under the sun you're gonna have like a what's that Perl language that is just all white space. I forget what it's called. It might just be called white space, but oh yeah. Okay, so it actually has the white space version. Yeah. So everyone who has like a pet language is going to implement Fibonacci. That makes a whole lot of sense. Well, I'm feeling better if like the entirety of Reddit's like, I didn't know the trick for this one. Oh god, what was I doing? Proc and offset, 0 time. Okay. So we need to set our starting time. So let's have this be buses hash 0 plus hash largest 1. And I did this because I didn't realize I was going to need the offset. I did not realize I was going to need the offset. I put it into a little lambda to automatically calculate for me, and now I actually need it. So now my data structure looks incredibly ugly. So that the last iteration we ran would never ever run. Okay, so we're starting off with 183. Let me just do a little sanity check. God, why is this weird like that? Okay, so we print out just so we're making sense here. Okay, this all looks correct now. Glenn, I feel much shame, but I think I need that redacted. I think I need the redaction. I honestly don't have an idea outside of brute force of how to do this one. I feel like that I could spend like 20 hours on some sort of fumbling with algebra trying to find a solution, and it's not going to come to me. The Chinese remainder theorem. Okay, let's see what this is about. I've never heard of this before in my life. Let's just look up the Wikipedia first. In number theory, a Chinese remainder theorem states that if one knows the remainders of the Euclidean division of an integer n by several integers, then one can determine uniquely. Or you still need to figure out how to reformat the data so it's usable. Okay, good. So it's not just like free now. That's good. One can determine uniquely the remainder of the. Okay, so you can determine the modulus by the product of those numbers under the condition that divisors are pairwise coprime. I don't know that term either. A set of integers can be called coprime or set-wise coprime if the greatest common divisor of all the elements of the set is 1. Okay, so if they're all prime, right? Oh, so 6, 10, 15 are coprime because 1 is the only positive integer that divides all of them. Okay, that's fair. They're not necessarily prime, but just based off of different. They don't share a common prime outside of 1. If 6 was not part of that set, they would not be. They would not fit that criteria. The earliest known statement of the theorem is by the Chinese mathematician. Okay, I don't care about the history. The history is dumb and whatever. I don't care. Okay, let's just get to the proof. Or do I even want the proof? I want to see how this works. Suppose x and y are both solutions to all the congruencies. Is there like a simple Wikipedia page for this? do I get like the Wikipedia for Dummies for this one? The existence first proof. I found a few different descriptions of, and the only one that made sense for me was from brilliant.org. Okay. Oh, is this a subscription site, Glenn? I am new to brilliant.org. This is new to me. It has paid content. Yeah, but let's see if we can get in here. Okay. So it looks like this page, at least, is not behind a paywall. A unique solution to simultaneous linear congruencies and coprime moduli. Basic form from the point P that when divided by some given divisors leaves given remainders. Given pairwise coprime integers. Okay, so given a set of numbers that when all together they do not share. Nice. I'm really glad that this one's free at least, because I do not have a subscription to this service. Would you say it's generally worth? Would you plug it, Glenn? I've never heard of brilliant.org before. So given that n sub 1 through n sub k all only share the prime divisor of 1, and arbitrary integers a sub 1 through a sub k in a system of simultaneous congruences. I don't know what that means by simultaneous. congruences. I think I need a definition. Okay. Define. Okay, a set of simultaneous congruences is a set of polynomial congruences. What is a polynomial congruence? What is a congruence? Can I just get the answer to that? What is a congruence? Math. Congruence math. Okay, so I know what congruent means. It means that the two shapes are kind of like a multiplier of one another. They're roughly equal. It's like equal, but more so. Okay, okay. System of simultaneous congruence, such that there's p sub 1x is 0, p sub 2x 0. Okay. Simultaneous linear congruences instead of linear congruences. Okay. Such that. Okay, let's just get back to the brilliant.org solution for this. Seven is congruent to modulo 5. Okay. Okay, that. Okay, that makes sense. That makes sense. Makes sense. Okay, Glenn. Thank you. That 7 mod 5 is the same as 2 mod 5. So therefore, 7 is congruent to 2 with respect to mod 5. Okay. I'm lucky that I chose a language that has inverse module built in. You might have to implement Euclid's extended algorithm. I might have something in the math library to give me that for free, possibly. I'll figure out when I get there, I guess. Allowing the general construction to is okay, compute n1 times n2, so on to nk. For each I1, 2, k, compute, okay. For each I, compute inverse y sub I mod n. Its extended algorithm. Yeah, exists. Kind of reading to myself here, trying to make sense of all this. When a system contains a relatively small number of congruences, an effective process exists to apply the Chinese remainder algorithm. Theorem. Of the problem. not sure if I'm familiar with this operator actually. I guess it's saying that x is congruent to 1, mod 3 is congruent to 4 mod 5, 6 mod 7, I guess. Congruence with the largest modulus. Rewrite the congruence as an equivalent equation. So x equals 7j plus 6 for some integer j. Okay, now we're getting closer to kind of like talking about here. What this is getting closer to the problem we have, because we have this kind of like thing of 7 would be like the bus time, j would be whatever multiplier we're looking for. X is t, the time. Substitute this expression in congruence with the next largest modulus. Solve. Okay, so 4 mod 5, therefore 7j plus 6. I'm gonna Google symbol really quick and make sure that the assumptions I'm making about it. I already paid you, Wikipedia, on a different account. Stop bugging me. Triple bar is a symbol with multiple context-dependent meanings. Refer to it if and only if. Active, also called material equivalence. Okay. Oh, so it's the same. It's this symbol. Okay. So it's if and only if, basically. Okay, so we're basically saying that we have a system of congruences, which is 1 mod 3, 4 mod 5, 6 mod 7. Okay. Okay, this is all starting to make sense to me now that I'm kind of getting my head around the notation part of this. Substitute expression. Congruence the next largest modulus. Oh, for the congruence. Okay, so we start off with a x is a value such that 4 mod 5 maps to 7j plus 6 equals 7j plus 6 is also 4 mod 5. Okay. A little tricky just because of the some of the notation I either haven't worked with in a very long time, or we use slightly different notation in my classes back 20 years ago. Good grief. I guess not strictly 20 years ago. We're talking 15 years ago. So it's been a minute. It's been a long minute. Okay, so 4 mod 5 comes from here. In this notation, we're basically saying when mod 5, we have a remainder of 4. I think that's what we're saying. And so we're trying to solve the case where we have mod 3 gives a remainder of 1, mod 5 gives a remainder of 4, mod 7 gives a remainder of 6. And obviously that translates into this kind of like a 7j plus 6 equals x algorithm. That makes sense. So a number such that that's mod 5 is 4 is same as this algorithm, which is the same as this is the same as mod 5 remainder 4, because we're saying these all have to match. And solve for the congruence. Not sure why j is a number such that mod 5 has a remainder of 4. I don't really get that part. I personally use steps from the section above this with the summation they put in step 4 of theorem, part of theorem proof. Okay, let me go up then. Okay. Okay, so we'll just start from the beginning then. I should have skipped ahead, I guess. Following is general construction of a solution to a system of congruencies using the Chinese remainder theorem. N is so this is easier for me to read now that I realize that A1 is the remainder we're looking for, is the remainder here. The one at a time can help you understand the theory, but it'll be harder to code, I think. Yeah, I agree with that also. I'm gonna need a general algorithm to finish this up. But understanding the theory is like really important because I don't know if I get the theory yet, so the theory is like the first step for sure. Compute. What exactly is N? It has the solution such that given a pairwise coprime positive integers and arbitrary integers, the system of simultaneous congruencies such that so the n's are bus identifiers, a's are like their indexes in that we come across them, as solutions such that the product of all of them together, big N. I don't know if big N is valuable here. Maybe. I'll just go through this. Compute big N equals the sequence of n times n to so on to k for each I as a series of 1 to up to k compute. Yi is big N, so the product of all of the the 1 the product of all of the bus times. You'll pop big N in a few formulas. Okay, that's good to know. So big N is essentially the product of all of our bus IDs, right? That because if N1, N2, and K, yeah. So that's the product of all of our bus IDs. Okay. So yi is going to be the product of all of our bus IDs divided by the exact bus ID we're looking at, and that's the same as the sequence of bus ID in the next one, all multiplied together, up to K. And K is the total number. Okay, so NK is the total sequence. So it's a product. So if we pick out any n, any bus ID in our sequence of bus IDs, if we take big N divided by that bus ID, it's the same as multiplying all of our things up until... okay. So this is very obvious. This is just saying that if we divide N1, it's no longer in the list of products. If you multiply everything except for I, Ni, it's the same as the big N minus, divided by Ni. Okay. That took me a minute to understand something that's very self-evident. For each I going up to K, compute C. Okay, I don't actually know what Euclid's extended algorithm is, so I might need to look that up real quick. I know that Euclid generally is about various common factors and stuff like that, I think. It has something to do with that. So if you flip over I, if you flip over Y, so it becomes some sort of one of our bus IDs divided by the product of all of our bus IDs, and then modulus it by that bus ID. Well, can I just like do modulus? Do I need like a special type of modulus for this though? Oh, more Wikipedia. Modular multiplicative inverse. In mathematics, particularly area of number theory, a modular multiplicative inverse of an integer a is an integer x such that... Okay. So ax congruency 1, congruency to... Okay. So the z equals y inverse mod n translates to yz equals 1 mod n. Oh, okay. So when you say 1 mod n, do you mean like literally like 1 mod n? Or because sometimes the notation kind of looks like for instance, if I look on here, where's the brilliant? Like here, I kind of get the idea that x mod n means if you take this value, or actually, let me just x equals a mod n. That means x is a value such that if you mod n it, it ends up with a. Is that accurate? Is that what we're talking about here? When you say yz equals 1 mod n, are you saying that yz, if you mod n it, it has a remainder of 1? By the way, it's still going. Just in case anyone was paying attention. This is still going. This will never end. It is getting slower, though, I think. I think it is getting slower. We get back to this article. Short way of writing the statement. M divides evenly the quantity. Oh, okay. So this is x congruency 1 mod m means that it has, if you mod m it, it has a remainder of 1. Okay. The remainder of m. Okay. If A does have an inverse modulo m, there's an infinite number of solutions for this. Do I need anything more of this? I don't think I do. I think that was just to explain the notation to me. Oh, we have the extended Euclidean algorithm here. Module multiplicative inverse A mod m can be found in Euclidean algorithm determines the greatest common the GCD of two integers, say a and m. Okay, yeah, I knew that. What does the extended form mean? If A has multiplicative inverse modulo m, the GCD must be 1, right? Okay, I'm getting back in. I'm going to go back into the other article, I think. Okay. So. Okay, so we did confirm what we were thinking about this notation here. Oh, so YZ. So this notation right here, this is where we were at. Y times Z. So this. And we're looking for Z. Mod n plus using not mod n1 ni rather using Euclid's extended algorithm. C1 exists and or pairwise. Let me actually look real quick first to see if we get this for free anywhere. Okay, so we do have a. I'm not sure if I understand the difference between the extended algorithm and the normal algorithm. We're wandering a lot today. Extended algorithms and computes in addition to the greatest common denominator the coefficients of Bezout's identity, which are integers x and y such that okay. So the way this works, grab this real quick, and we might need this. We might need this, so let's just grab onto this. Give credit where credit's due. Okay, so let's assume that we have an extended GCD here. Let's go back into... Not here. Back to here. The integer x in the summation of a times y times z. Z is this thing we're getting from Euclid's. Y is just it divided the multiplication of everything divided by n. And what's a? A is our index. It's like our remainder that we're working with for this I. Okay. Okay, so I understand how to get A. I understand how to get Y. Z is the hard part, I think. Okay. So for that we need find a Z such that Y times Z has a remainder of 1 for that n. So does Euclid's just give that to me for free somehow? Given non-negative numbers, I'm over here now. Given non-negative integers a greater than b, compute coefficients s and t such that GCD, the greatest common denominator of a and b, is s times a plus e times b. So let's make a new notepad because this old one's trash. It's irrelevant for anything we're doing now. How does GCD give us? That's the part that I guess I'm struggling with right now. DI exists because since N1, N2, and K are all pairwise for prime. For X, I feel like this is hand wavy. This feels hand wavy to me. Let me look into the next sections. Well, okay, let's look at the example. Or no, this is a proof. DYX is a solution. I often don't like looking at proof because usually I don't care. I want to trust that the mathematician that wrote a book knows what they're talking about, and I just want to take them at face value most of the time. uh, I mean, we can substitute in some things, I guess. This basically means Zi equals right. That's essentially what this means. Or actually, maybe it's 1 over yi. I think. And it's not times, it's odd. Wait, no, I'm screwing this up. This is not correct at all. Wait, no, that. Roll up a little bit. Now that I've read through that, maybe going through the solving section will make more sense to me. Okay, so we have mod 3 with a 1, mod 5, 4, mod 7 with a 6. Begin with the largest. Let's just follow through step by step, I guess. J in this case. Oh, J is like our unknown. We'll use X instead of. Just a little note there. 7j plus 6, same as 4 mod 5. We know this because of our algorithm above, because of our definition above, our system of equations. Then solve for the congruence. Solve for the congruence of j. J for mod 5. Okay. How do we know that j equals 4 mod 5? We know 7j plus 6 equals 4 mod 5. I guess that's the step that seems kind of weird to me. That's, I guess, on this solution, that's kind of like where I'm getting a little stumped, because why is j congruent with 4 mod 5? Is it something with congruence where you just drop all the pluses and the multipliers, and you can just do that? Oh, j is 5k plus 4? Okay, I'll buy that. I mean, wouldn't x also have to be, though? Because if x is congruent to 6 mod 5 and x is congruent to 4 mod 5, there's like a... And we're looking for the same x. That has to be the same thing, right? Yeah, I'm just gonna run with it and assume that j does equal that. J equals 5k plus 4 for some integer k. I mean, that's fair. If we concede this point here, substitute the expression j into the expression for x. Okay. So we already know that we're going back to our x equals 7j plus 6, so that means (5k plus 4). Then x equals 35k plus 34. Yeah, I buy all that. I trust that arithmetic is correct. Basic distributive property at that point. I substitute this expression of x, final congruence. So our final congruence was x 1 mod 3 So 35k plus 34, 1 mod 3. Yep. Well for k. How's that turn to 0? I think there's fundamentals about arithmetic with modulus that I some properties of modulus that I don't understand here. Oh, I get it. I get it. So if you... No, I don't get it. Okay, so 1 mod 3 equals some expression minus 1. So if you add on to both sides, you end up with 36k. And 36k mod 0. And multipliers just drop off. That part makes sense. Okay, write this congruence as an equation, and then substitute the expression k for the expression x. k3l for some integer l. Oh, right. So this equals the equation k equals 3l because we know that there's never going to be there's some thing that can be multiplied by 3 and end up because it divides evenly. Okay, so if we go back to this guy up here, x equals 35k plus 34, 3l plus 34. Okay, x equals 105, l plus 30. Okay, that all makes sense. So x 34 mod 105. So that's a... So does that mean that 105 plus 304 is... plus 34 is the first one these all have in common? Broke for me. Did you give up on the previous section? Still doing it. Oh, shit.